we continue our discussion on file organization. We have discussed what is a simple heap file or a pile where data is stacked one on top of the other. Then we saw what are sequential files in which the data is organized in terms of the primary key. It is organized blockwise so that insertion and deletion is done easier by leaving some free space in every block for insertion and maintaining the next and available pointers. In order to facilitate faster searching, we discussed the concept of indexing, which is same as the concept of having a table of contents in a dictionary, in which we maintained another file which was called the indexed file. The index file maintained some of the primary attributes, and based on that we did something similar to a binary search, not exactly a binary search, but something similar to that. A part of it was a search based on the index and a part of the search was sequential. We saw several types of indexing, namely dense indexing, sparse indexing, indexing based on multi-level stages, that is, instead of having one index file we had levels of index files, 2 or 3 levels of index files. We also saw the difference between indexing on a primary attribute and indexing on a secondary attribute or a non-primary attribute. One is called primary indexing, the other is called secondary indexing. We can have simultaneously more than one indices, and we can access the file according to whichever index we want. We can update the file whenever we insert or delete. We will have to update the indices. We can also have a mixed mode of operation in which we have a fixed index file which is done, and then whenever we have to insert a new element we introduce it in another heap or a pile, and we do not update the indexing. Whenever we have to delete an element we just mark the bit 0, and in such a situation we do not update the indexing until reorganization is done. And what we do is we access the file according to the indices, and if we don't find it there then we look into the additional secondary heap area to see if it has been newly inserted or not. So we can use a mixed mode also, and during reorganization we will convert all the heap elements back into the index sequential file and maintain an index. Depending on the situation we will perform whichever operation we want. Next we will look into what are called B plus trees. Now they are B plus trees. The concept of a B plus tree must be well known to those who are conversant with balanced binary search trees in programming and data structures. It is one of those balanced binary search trees which helps us to easily perform operations insertion, deletion and find on objects which are on the memory. But here we are discussing data which is available on the disk, and therefore there will be subtle differences between a B plus tree which is there on the memory and a B plus tree which is there on the disk. But the similarities are obvious, and therefore the name remains to be a B plus tree index file. The motivation. Suppose we have a 2-level indexing. This is one index, this is the secondary index, and these are the data files. The question is, during insertion and deletion, initially when we have the indices, the data may be organized in such a way that when we access here there are 10 elements. Each such field points to 10 elements which have to be scanned sequentially. But after a sequence of insertion and deletions, this may become skewed in the sense that some of them may point to a large number of files which have to be sequentially accessed, a large number of records, while others may actually point to 1 or 2 records only. So what will happen is that due to, even if we assume uniformity of accessing, more of the calls will relate to files which are to records which are essentially maintained in a sequential order, and this indexing will not actually be as balanced or uniform as we expected it to be. Options are to make more than one levels, but then updating these levels so that this is maintained balanced as much as possible will require the number of levels to be dynamic. The number of levels will be dynamic, and so that each of them accesses nearly equal number of records in a sequential manner. In order to do this, we will borrow our ideas from whatever we have in binary search trees. Let us see the correspondence of this searching to searching in a binary search tree. In a binary search tree, suppose we insert some numbers. We insert 5. The smaller number is inserted to the left and the larger is inserted to the right. So if we insert 2, then we may insert 7, then we may insert 9, then we may insert 8, then we may insert 12, then we may insert 1, then we may insert 4, and so on. This is how we maintain a tree, and we search it. If we have to search for 8, we see it's greater than 5, we come here. Greater than 7, we come here. Less than 9, we come here. If you observe a little, you will see that the concept of multi-level indexing is the same. If you want to search for something, you come here, get to it, then you come here, go to it, you come here, go to it, and so on. It is similar to a binary search tree in the sense that you do searching based on certain pointers and less than equal to relationships. If the element which you have to search is less than this and greater than this, then you go along this pointer. Therefore, we would also like to maintain the number of levels so that we have what are called the tree is balanced. Let us look at a binary search tree here. This tree will be balanced if there are n nodes. A tree will have height no more than log n. Then the tree will be said to be balanced. Height means the length of the longest path. Now, if we insert arbitrarily, then if I give you numbers 5, 7, 9, and the numbers come in strict sequential order, then this tree will become skewed and not balanced. And searching for any element will not be as efficient as we expected it to be. In order to balance such trees, we have various balancing schemes and various balancing algorithms. And in data structures, we have the AVL tree, the 2-3 tree, the B tree, the B plus tree, the red-black tree, and so on. Similarly, in a multi-level indexing scheme, if we have to do balancing, then we will have to use those ideas which are similar to ideas in algorithms. A structure which is similar to the B plus trees in algorithms will be used here. So these are called B plus tree index files. So the structure of the indexing will not be sequential but be like a tree. Now each node of the index will be the size of a block. One block. Now in one block it will store the following information. Suppose it is doing according to a primary key. It is doing an indexing according to a primary key, say accession number. Now this block may hold 10 records or 20 records. We will have k records and k plus 1 pointers to blocks or records. For example, here we have got these records. K records means each record corresponds to a key attribute. suppose we have got accession number. And here we keep two such accession numbers and 3 pointers. This will point to those records which are less than 5732, less than. Let this be our convention. This will point to those which are greater than or equal to 5732 and less than 5384. 5272 and less than 5384. And this will point to those which are greater than or equal to 5384. So this is one node. Since in a normal 2-3 tree or B plus tree, we can have, depending on the size of these records of the size of the primary key attribute and the size of the pointer, we will decide how many such we will keep. We can keep 3 and 4 or 5 and 6, 3 values and 4 pointers, 5 values and 6 pointers, and so on. So the structure will be, for example, we will have a structure like this. Now this one is the top level start of the B plus tree. It has got two key attributes. This is say accession number 124 and 7352. Always this will be less than this. Always this will be less than this. This will be less than this. This will be less than this. This must be true. Then this means that all those which are here, the records which are here, are between 124 and less. Here means this is less than 124, our convention. This is between 124 and less than 7352. And this is greater than 7352. Greater than or equal to 7352. And let us say this is null for the time being. This may be. Here it says this points to those records which are less than 21. This is greater than or equal to 21, less than 110. This is greater than or equal to 110, but obviously less than 124. Because this side itself is less than 124, all of them. So even if it is greater than 110, it must be less than 124 by definition. Here it is greater than or equal to 124 because it comes from here, but it's less than 175. This is between 175 and 1123, and this is greater than 1123, greater than or equal to, but less than 7352. So you will have several such, and you will go down, 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 and then you will have what are called the leaf nodes. In the leaf node, you will have, suppose we take dense indexing. in dense indexing, and let us assume that we are working with dense indices. Then in the dense indexing, suppose we have 0, 1, 0, 3. Somebody will point here, somebody will point here. Dense means this points to 0, 1, this is 0, 3, and this is the last level. So in the last level, we will make this one point to the actual record. This will point to the actual record, this 0 starting with 0, 1. 0, 1, and then what are the other attributes. This will point to the record 0, 3. It may be in the same block. This is the base data file, which may be a sequential file. This is the base data file, which may be the sequential file. This will point to 0, 1, this will point to 0, 3. This is useless actually now, because there is nobody which is greater than 0, 3, because there is no 0, 2 allowed. These are leaf means if this is 0, 1 and this is 0, 3, there is no 0, 2, because we are following a dense indexing scheme. This will point to the 0, 5, this will point to 0, 6 record. So we can make use of this to point to the next record in the leaf node section. We will make the last pointer of a leaf node point to a record like this. All right. Logically, how you will declare such things is also slightly different, because these do not point to structures like this. These points to blocks. So here this can also only point to a block. And if it points to a block, in that block you will sequentially access it to get the 0, 1. This will also point to the block where 0, 3 is present. This will point to this one. So let us go back and see what we have in the leaf node. The leaf node structure of a B plus tree. Let us, for sake of change, take a B plus tree which is got many. So this is 0, 1, 0, 3, 0, 4. This points to, this is a leaf. This points to block for record with key 0, 1. Similarly, this points to block with record for record with key 0, 3. This points to block for record with key 0, 4, and this points to the next leaf node. This is a leaf node. For a leaf node and in a dense indexing scheme, less than 0, 1 means there is only one. So we take the convention that for a leaf node, this will point to the actual block. This will point to the actual block, and this will point to the actual block. This is the convention we follow for a leaf node, and this will point to the next node. So this is a leaf node in the B plus tree. A non-leaf node in a non-leaf node, this will point to the next either leaf or non-leaf node. That is, this will point to block with index block, that is this is an index block. This will be an index block which may be a leaf or non-leaf. For records with key less than 0705, that is our convention. You can take less than equal to also, but you have to take a common convention. Similarly, this will point to an index block which may be a leaf or a non-leaf for records with key greater than equal to 0705 and less than 1137. This will be pointing to those between 1137 and 1736, and this greater than equal to 1736. These three will have to be sorted, and the final property, which is the most important property, the very important property here is that all index blocks have to be at least half full. What does this mean? This means that suppose I have only 1 or 2 records, then I need not have all these values. That means this may be null and this value may not exist, but I cannot have it such that all values do not exist. If all values do not exist, then obviously this node has no meaning. In this particular case, I am not allowed to have only one value and two of, that is, one pointer is okay and 3 of them are nil. This is not allowed. At least 2 pointers of the 4 must point to a valid place. That is, 2 of the pointers, at least half of the pointers, must point to valid index blocks. If I have got only 2, then of the 3 pointers, 2 of them, half means greater than equal to half. If I have got only 2 such, in which I have 3 pointers, then I cannot have 2 pointers to be null. I can have only 1 pointer to be null in the worst case. Either all 3 pointers will point to valid blocks, or at least 2 pointers will point to valid blocks. So if I have got k pointers, then at least k by 2 pointers, ceiling, k by 2 ceiling must point to valid blocks. What does this mean? This is not allowed. This is pointing to another one. This is not allowed. Even if this points to valid blocks, this is not, such a node is not allowed. That is a core idea behind B plus trees. And obviously it is a search tree according to the definition here. It is a search tree. So let us see how we do insertion and deletion in a B plus tree. Let us say we have initially nothing and we do insert 73. So once we insert 73, we will create a block. For the time being, we are using 3 pointers and 2. So we will create a block. This will be a leaf block, and this will point to the actual record. Here we have got the data file. So this points to 73. In such a situation, we have nothing to do. Actually, there is no concept of an index here. This index is futile. So we will put in one more element here. Let us put in one more element, 108, and this points to 108. Let us put in another element. At this situation, we may have many things to do. We may put in another element 115, which will be pointed here. But let us say we put in an element 100. If we put in an element 100, what will we do? We will replace this by 100. We will make this point to 100 and this point to 108. So I'll just redraw the situation. We had 73, 108, this was pointing somewhere, this was pointing somewhere, and this was a leaf node, this was null. Now we have introduced a new record 100. This is a leaf. So we have to add another leaf node. So where will this, where to add it if we have to find out? We will search here. This is the only index record. Come here, this is a leaf node. It is greater than 73. We will come here, it is 108. We will go here and see that this is a leaf node. So there is no 100 record. So that record has to be inserted. And I cannot insert it here. I just cannot insert it here. If I put 100 here, then 108 has to be placed somewhere. So I malloc, or I get another block. And so now I have got two blocks, both are leaf blocks. This points to 73, which is the smallest. This points to 100. This points to 108. And these two are nullified. The rule of null is not no problem in case of a leaf. In a non-leaf node, we must have at least one of these values here. But this does not mean that we have got our tree. We have to have, whenever we have two, we have to have a parent of the two. There must be a root of the tree. So here we will now malloc another one and get the root. Now in this root node, we will have to place a value here and a value here. The value here, since we have taken the convention that all nodes which point here, this will point here and this will point here, this will be grounded. All nodes here must be less than the value here, and this side will be greater than equal to the value less than the value here. So what value we must put here? It is the minimum on this side. It is the minimum on this side, so 108. And this value may be nothing. We don't know. This value is not there. But two pointers are definitely there. For a non-leaf node, you must have two pointers. A non-leaf node with a single pointer does not make any sense. So we have got, once we insert 100, we have this structure. So at this point, let us say I want to insert 105. I say 120. So I'll come here, I'll come here, 108 null. So 120 does not exist. I will peacefully put 120 here and make this point to 120. Search is like binary search. You come to a record, come to the start, see the first key. If it is less than the first key, then call it recursively this side. If it is greater than equal to and less than equal to the second, then you call it here, otherwise you call it here, or it is not available. And on a leaf, you just go directly to that record and access that record. Now suppose at this point I want to introduce 125. I will come here, 125 must come here. So if 125 must come here, then this will overflow. So like I did when I inserted 100 here, I will replace this by 2. So I will replace this by 2 elements. One will be 108, 120, and another will be 125. Here, since 125 is beyond this, I do not need to change anything here. I will just add another one with 125 and put it here. I need not update anything here because this is minimum this side. Since this side is null, the value here will be the minimum pointed here. Alright, the value here will be the minimum below this, the value here will be the minimum here. So after that insertion, my tree will look like this. This is the situation. I first inserted 73, then 108, then 100, and then I got this structure, then I inserted 125. Suppose at this point I get insert 105. Now where does 105 occur? 105 will occur here, less than 108, so it will come here. And I have to introduce 105 here. So once I have to introduce 105 here, I will leave this as it is, 73, 100. I will definitely put 105 here. This is what happens at the base level when I'll search down here, find that I have to insert it here. After this, so I will insert one node here and move these pointers like this. And I already have this structure, this points here and this points here. Now this one must have a parent. Now this parent, normally I have got, this one is pointing here. This one is pointing here and this one is ground. This is the structure at this point. Now actually I want this to point here, but this record must also be pointed from this point. So now I will have to have somebody pointing here, and this one I will have to have pointing here. So what I will do is, since I have got this to be null, I will shift this pointer here, this here, leave this here, and this will now be 105, the minimum here. This will now be the minimum here, 108, and I will have this structure. Now if I insert another node, say if I insert 106, then I can peacefully insert it here, 106, and this pointer will now point to 106. But if I insert say 107, which will be inserted here, somebody must point from above here. There is no pointers free here, so I will have to generate another node. I will have to generate another node, shift them, make 105 and something here, some portions here, and since these two are now, since I have split up the root node, I will have to generate another root node. This is how the whole process will go on. We will discuss these algorithms in details about how to do insertion, and then we come to do how to do deletion. But the idea behind a B plus tree is that since these pointers will at least point to 2 or 3, the height of the tree will be between log 3n and log 2n. Since these will point to, since any such node will have at least 2 pointers, the height cannot be more than log 2n. Obviously, it will never be less than log 3n because we cannot have more than 3 pointers. And therefore, the time of search can never be skewed and become order n. The indexing, the tree will always be balanced. So we will see the details of the algorithms for insertion and deletion again for B plus trees in the next class.